Okay, people, let's keep going down the rabbit hole. Learning goal number 3 here. Know the acceptable wave functions with spin for all closed shell atoms. All right, let's do it. So, revisiting the Pauli principle and the Pauli exclusion principle, we recognize that when we change the labels of any two identical electrons, the wave function must change sign if those two electrons are spin paired. So looking at our sigma plus and sigma minus state, we want to exchange those labels and test if we get this result. So we'll first do that on the sigma plus state by writing sigma 2, 1 and just exchanging the labels. So now that becomes alpha 2, beta 1 plus beta 2, alpha 1. And if we make a quick inspection here and recognize that the order of our wave functions doesn't really matter because they don't contain operators, then this is the same thing as the sigma plus 1, 2. So this state can't be used to describe a pair, a spin pair of electrons. So let's do the same thing on the sigma minus state. We'll write sigma minus 2, 1, and we'll switch the position of those labels. So now that becomes alpha 2, beta 1 minus beta 2, alpha 1. And with some odd algebra here, we'll see that this does it. So I'm going to factor out a negative sign from this. So factoring out a negative 1, and that's going to give me the following: negative alpha 2 times beta 1 plus beta 2 times alpha 1. And recognizing that the order of these doesn't matter so much, I'm going to write this as, again, negative 1 over root 2. And now this beta 2 alpha 1, I'm just going to write that as alpha 1 beta 2, because again, it doesn't matter if I change the order of the wave functions. And then now that's minus, and I'll write that as beta 1 alpha 2. And hopefully what you can see, what we ended up with now is just negative sigma minus 1, 2, right? There it is. There's the sigma minus 1, 2 state with a negative sign in front. So what this means now is this sigma minus state is acceptable to describe a pair of electrons. Well, what about all these other spin wave functions that we came up with? So remember, we've got a whole bunch of these possibilities that we came up with to describe any two electron system. And those are going to go as the following. So we're going to have psi 1, psi 2 times alpha 1, alpha 2. So both electrons spin up. We can have psi 1, psi 2, beta 1, beta 2. Both electrons spin down. Or we could have the following. We could get psi 1, psi 2 times the sigma plus 1, 2 state. Or we could have psi 1, psi 2 times the sigma minus state. And as it turns out, right, this one is the only acceptable wave function with spin to describe a pair. So I'm going to call that a singlet state, which is a pair of electrons. And then now you notice we end up with 3 other possibilities that could describe still a 2-electron system. And as it turns out, that 2-electron system would correspond to unpaired electrons. So 2 upspin, 2 downspin, or like this superposition of possibilities. And we refer to this as a triplet state, where it could be both spin up, both spin down, or some combination of those two. So again, a singlet state describes a pair of electrons. That's the only way that it can exist. There's only one way it can be to be acceptable for Pauli principle. Or we could have both anti-parallel, which, as it turns out, is a triplet state. There are three possibilities to describe that state. So now if we want to come up with some like shorthand notation to describe this, we can do the following. So our acceptable wave function for helium becomes this determinant. Okay, determinant, where we have our normalization constant 1 over root 2, and now we make a matrix of all of our possibilities. Psi 1 alpha 1, so that's one single electron being spin up. Psi 2 alpha 2, so this is now the other electron also being spin up. Psi 1 beta 1, so this is that same first electron, but now it can be spin down. And Psi 2 beta 2, the other electron, and now it's spin down. And if you recall, the way that these determinants go, right, we'll multiply this term by this term, and then take the difference of that term times that term. So let's do that. Let's go ahead and do that determinant. So we've got our normalization constant, 1 over root 2 times, and so now that's going to go Psi 1 alpha 1 times Psi 2 beta 2. So let's just write all that out directly. Psi 1 alpha 1 times Psi 2 beta 2. And then now for the determinant, that's going to be minus Psi 2 alpha 2 times Psi 1 beta 1. Okay, and so now if we do some algebra on that, I can factor out a Psi 1 and a Psi 2. So I'll end up with 1 over root 2 times Psi 1 times Psi 2. And now distributing that back through, I have alpha 1 times beta 2 minus alpha 2 times beta 1. Well, all of that equals the sigma minus state. Thus, we can see our acceptable helium atom wave function is the following. We have the wave function of electron number 1, and in the orbital approximation, that could just be a hydrogen 1s wave function. We have the wave function for electron number 2, and once again, in the orbital approximation, that could be just another hydrogen 1s wave function. And then now we also have this spin wave function to describe that pair. So that becomes our acceptable helium wave function. Any of these other possibilities, those triplet states, could describe a 2-electron system, but that 2-electron system has both of its electrons unpaired, or, the spins are parallel. So now what about any closed shell? Well, as you might imagine, we can make this quick jump using this linear algebra operation, where now we're going to put labels to indicate the orbital. So this letter Z right here describes an orbital. So we could start with orbital number 1, for example, Psi A, electron 1 with spin up. We could then move that over to electron number 2, electron number 3, and eventually some nth number of electrons. So n corresponds to the number of electrons. And then, of course, we have to have another line describing that same orbital, but now all spin down, right? So Psi A1, this time spin down. Psi A2, spin down. Psi A3, spin down. All the way to however many electrons we have. Once we've satisfied that orbital, we can now move down to the next orbital, B, and repeat the process, right? We'll have Psi B1, alpha 1, Psi B2, alpha 2, all the way out to the beta possibility, right? I should have wrote that as, I should have kept all these as like alpha, right? Keep them going, alpha, alpha, and then the next possibilities would be beta, beta, all the way down to our zth orbital, okay? And then notice that our our normalization constant becomes 1 over n factorial, so the number of electrons we have. So this Slater determinant, that's what this is called. It is called a, let me make sure I'm spelling it correctly. So this is called the Slater determinant, and it is the basis for one of the more famous types of computational chemistry methods known as Hartree-Fock. So the Hartree-Fock computational method is dependent on coming up with one wave function to describe a closed shell species by computing the determinant of this matrix. And as we might imagine, that does require a supercomputer to do so. Okay, folks, so I'm just going to kind of talk briefly about computational methods as we go, only very briefly, and hopefully those will have some familiarity to you from your molecular modeling course. Okay, I'll see you in the next video.